Thank you. So how many of you are here for the first time? Awesome. So great to have you here. So as Shasha mentioned, so we are an early stage investor. We are a studio that creates companies focused on data-driven applications use cases across a variety of themes. So we are not a kind of opportunity-driven fund. Opportunity-driven fund is they hang a shingle and say, I got money. And so they take 100 meetings a week. And so theme-driven is like our folks are kind of researching, IoT online enterprise, different verticals, different domain areas. And in the course of that, we may find two girls and a dog, or we may start a company ourselves and recruit founders. So we have a number of companies that we have done in this space. Some of you are probably familiar with them. So they range from IoT, ambient intelligence, cybersecurity, AML and KYC for blockchain, and so on and so forth. Augmented reality, and so on and so forth. And probably many of you know our former CTO Lance Riddell, who also worked at Yahoo on Hadoop. And so he sold his company. He started a company with us called Kosei, that's part of Pinterest, and recently we sold another one to Rakuten. Our startups are hiring execs, so this time I'm not going to feature engineers, but execs. So Foghorn is looking for a VP of product management in the industrial IoT space, and Coinalytics is looking for a CTO who has a combination of crypto and big data infrastructure background. We recently had our annual summit, and so hopefully you recognize some of these people there. And so two of these speakers, Harel Kodesh, who's the CTO of GE Digital, and Adam Beck, who's this founder and I think president of Blockstream, are going to be speaking at a public event in February. So stay tuned and you'll find out more. So be a part of the conversation today. So tweet using the hashtag. And with that, I'd like to introduce Mike Percy. Mike Percy is at Cloudera and developed Kudu that you're going to hear about, a Columnar database that's native to Hadoop. And prior to that was involved with Flume and worked at Yahoo on HBase, Hadoop, and other things. And so we're extremely pleased to have Mike.
Thanks for that. Hi everyone. Let me just quickly switch. Thank you, Ravi. My name is Mike Percy. I'm a software engineer at Cloudera. Cloudera is a software company that provides big data infrastructure, open source big data infrastructure, and management components on top of it. I'm here today to talk about Apache Kudu, which is a project in incubating Apache Software Foundation project. It's a storage engine that allows you to run fast analytics on fast-moving data. I'm a PMC member on Kudu and a committer. I'm also a PMC member on the Apache Flume project. Been at Cloudera for the past 4 years, and been working on Kudu for about 2.5 years. Prior to that, I was working on Flume. And prior to that, as Ravi said, I was at Yahoo, mostly working on personalization systems using big data technology. If you want to get a hold of me, you can. This is my email address and my Twitter, my Twitter address. I think that these slides will be posted, so if you want to get a hold of me, please reach out. So today I'm going to talk about Kudu, and this is the overall outline. Essentially, I want to talk about why build a new storage engine, why build a new open source storage system when there some use cases of why it makes sense, when it makes sense to use Kudu, some of the design and how it works, some performance benchmarks, and how to start using it or how to get involved. So 2 main things have occurred in the last decade or 2 that are really affecting storage systems and really leads into why building a new one makes sense. One is there are gaps in existing systems like HDFS and HBase, which I'll get into a little bit, and as well as hardware is evolving. So the existing storage landscape prior to Kudu within the Hadoop ecosystem basically consisted of HDFS and HBase. By a show of hands, how many people have used Hadoop or related technologies? Okay, maybe 2/3 of the room. Okay, that's great. Then, so essentially, for people who haven't, or just to give a summary of why this gap exists, HDFS, which is based on the Google file system paper from around 2003, is a system that is really good at doing batch workloads. So if you write some really big files and then dump them onto HDFS, you're going to get nice performance when you go back and read it, and you're going to get good throughput on reads and writes. But you're not going to be able to seek very easily, and you're not going to be able to update individual records. By the way, I'm hearing an echo, or other people hearing an echo as well? No? Okay, sounds good. HBase, on the other hand, is a layer on top of HDFS, but essentially what it's built to do is allow individual record access. So you can do inserts, updates, and deletes, but because of the way HBase is designed, scans are pretty expensive to do if you want to go through your whole table. So this is the gap that we want to fill. And so a few years ago, we started planning on what could be done to address this gap. Kudu is our answer. The goal is to have high throughput on scans when you're doing analytics on lots of data, but still allow for low latencies if you want to do inserts, updates, and deletes, and individual record access. Database like Semantics on a single row to start with, so essentially atomic row updates and reads, are something that developers want because it's hard to develop without those assumptions. And we really wanted it to be something that maps really well to SQL. Just makes it really nice to use through a traditional database interface without giving up the nice NoSQL APIs that we've become used to in the HBase world. So really quickly on the hardware side of things, since Google released their papers, a lot has changed. So back then, the disks that we're running on, spinning disks, aren't going to really give you very good latencies, right? You're not going to get lots of IOs per second. Same thing with RAM back then. Maybe you'd have 4 gigs of RAM on a server, maybe 8. These days, Flash is becoming cheaper and cheaper. You can get 500,000 IOs per second on read, and 250,000 on write. It's just getting cheaper every day. And so it's starting to be a viable solution, as opposed to a decade or more ago, it may cost millions of dollars to try to put something in Flash. More recently, actually just this year, Intel and Micron announced their new NVRAM technology, which is 1,000 times faster than NAND Flash, but still cheaper than RAM. So you start to get to some really interesting performance characteristics for durable solid-state storage. RAM along the same lines. These days you can get a server that has 256 gigabytes of memory, and it's not crazy. And our customers are telling us that they want to, if the software can use it, then they're happy to buy that hardware. So the bottom line is that CPU is really the remaining bottleneck for big data workloads, and there's been research that has shown that that's commonly the case.
Can comment on why? Why the bottleneck?
Why is that? It's because existing systems like MapReduce and HDFS were really built assuming that the disk is really slow or that you may not have a lot of RAM. So, but if the disk gets much faster, then essentially what you're doing is you're spending a lot of time doing data processing and basically doing things that didn't used to be the bottleneck. So once that's the case, once the storage and the RAM bottlenecks have been removed, you know, then that's what you have to address. So I just wanted to show really quickly where Kudu fits into the whole big data stack in the Hadoop ecosystem. So up at the top, for those of you familiar with the Hadoop ecosystem, typically there are, like Impala, for example, can be used to perform SQL access across heterogeneous storage systems. So down at the bottom you have HDFS as a file system, HBase as a NoSQL store, and now we've added Kudu as a relational store. So something like Impala can essentially do joins across these three systems. Same thing with Solar and Spark. These systems can access data in the storage layers and then essentially do processing utilizing that. So we're seeing more and more that the storage layers and the processing layers are being decoupled. So what we wanted Kudu to achieve is simplifying the architecture for certain use cases that are relational and analytic, but also be natively integrated with everything else in the stack, so it feels natural to use. Okay, so what is Kudu? Finally, it's a scalable, scale-out, tabular data store. So you have schemas and you have tables. It's designed to scale to thousands of nodes. Currently, we've tested it on a 3 petabyte cluster up to 275 nodes. It's very fast. You can do multiple gigabytes per second on a single node of read throughput. Many operations per second if you have fast disk for reads and for writes. But it feels like a traditional database while being able to scale to billions or tens of billions of rows. We provide APIs for C++, Java, and Python. We also, Kudu has a SQL-like schema, so you know, it's if you imagine a table having columns, you know, it looks like, it sort of feels like MySQL circa 10 years ago. Essentially, you get inserts, you get updates, you get deletes. There are no multi-row transactions yet. You can do fast alter tables. You don't have to take the table offline. You can continue running your workloads, and after a few seconds, the alter table will complete. You can have composite primary keys or a single primary key. And it integrates with a bunch of stuff already, and there's a bunch of stuff coming down the pipeline as well. So we have MapReduce integration, Spark, Impala. Apache Drill, the Dremio guys, came over and did a little hackathon with us a couple of weeks ago, and got that working. And there's more coming. Actually, something I didn't list here is also IBIS, which is another Python-based analytics.
So what is the bold-faced finite number of columns is trying to say?
Oh yeah, so Kudu is what we call a true column store. So because these columns are separated out into their sort of individual storage spaces, then you don't have the thing like in HBase where you have these column families that are actually, you know, their own storage space. But within that, you can define arbitrary keys and values and just, you know, define sort of column qualifiers on the fly. Kudu doesn't support that, so you alter your table to add a column and then you can insert.
So in that sense, it's more traditional relational.
Exactly, yeah, more traditional relational.
And what is the limit?
I think I mean, it depends on how you like what your columns are, but probably hundreds of columns, not tens of thousands of columns.
So does it support transactions?
Not multi-row transactions.
Yeah,
it's
that's
atomic on individual row, as of now. we want to add that eventually, but it's not going to happen this year. I mean, it probably won't happen in 2016.
So individually, when you say you are based on a row key and then you update, you can update only one transaction for
Your updates are atomic for a single row. So
One
you can
row.
do a bunch of changes, but those changes won't be committed transactionally across multiple rows, only on a single row.
Even if the SQL statement is actually mucking around with multiple rows.
Yeah.
Is it one statement or one row?
One row.
Wow.
Like similar to HBase, right? A lot of existing systems, big data, NoSQL systems, sort of have this play.
So this means that if you have a set-oriented update, some of it might succeed, the rest is like MongoDB in that sense.
I wouldn't compare it to MongoDB.
Yeah, but the point is, you're not even providing statement level atomicity. So if
Yeah,
it's
there are no
if it's a
multi-row
SQL
transactions.
statement which manipulates multiple
Right.
records.
Yeah, there are no multi-row transactions.
Yeah, so that's
So I'd like to talk about the use cases where Kudu makes sense. It's not going to be we're not looking to compete, for example, in OLTP workloads like Oracle, although a lot of nearly OLTP stuff might work pretty well. So Kudu is really best when you want to use the same database to allow for individual record lookups, but have really efficient scans. So, for example, a time series database. In finance, maybe you have stock tickers that you're tracking, and you want to be able to view the very latest stuff, like the current price of the stock. But you also want to be able to run big jobs to look at like changes over time of how the stock has changed. Maybe you want to use this to feed your predictive models in order to help you do trading or do historical reporting. Kudu allows you to do both of these things at the same time. Fraud detection is another good example of a similar type of use case where you need up-to-date data, but you also want to be able to run on a long range of historical data. Network threat detection, operational data stores like traditional sort of data warehouse workloads, a lot of them have a similar set of requirements. And if you don't need zero transactions for your use case, then we think Kudu would be a good fit.
Quick question.
Yeah.
In the fraud detection, would it support user behavior modeling as well?
Well, I think that like that. So the question was, would fraud detection support user behavior modeling? And yeah, that's typically something that's part of fraud detection, at least for like advanced systems, like pretty modern systems. I think they typically track your behavior, what you've done recently, and know that if you show up in a country you've never been to before and they don't see a record of you buying an airplane ticket, they probably flag it. So this is an example here of sort of that kind of use case. This is sort of a pre-Kudu use case. This is a pretty typical thing of where you want really efficient scans. So you essentially want to have most of the data in a columnar format, which I'll go into a little more later, of why a columnar format is beneficial. So Parquet is currently a very popular format for storing analytic data for analytics on HDFS. It allows very efficient scans of single columns of data, for example. So say you have your messaging system that's generating your events that you want to detect for fraud. Then these, in this case, you're inserting them into HBase. After a while, you decide, okay, I've accumulated enough records in HBase that it would be efficient for me to create a new column file to store in HDFS. So you essentially flush this data out of HBase, copied out of HBase, onto HDFS in a Parquet format in a big batch. Then, as part of that, you create a new partition, you wait for that job to complete, and then you probably go back and clean up the data in HBase and remove it. And then on the reporting side, you have to consider that the new data is going to be in HBase, but the old data is going to be in Parquet. So you have to find some way to join this. You You have to figure out at what point, what's the cutoff where there's stuff in Parquet but not in HBase. It's pretty tricky to do. It's doable. It's just has a lot of complexity associated with it.
So the basis for this is that HBase is good for ingestion but not good for queries?
Right, HBase is definitely optimized for writes in single record access, but yeah, not for
Queries.
long scans. Yeah. So a bunch of things to consider is, what if something crashes when you bring it back up? Are you going to lose sort of some consistent view of what's going on? Dealing with failures. What about delayed records? Maybe you have some offline process that's writing something from yesterday, but you want to report on something that happened yesterday, so you may have to look in a long time range to get, because it wouldn't be reordered, you may have to look for a long time range and then kind of sort it or filter by range, instead of just looking in the range that you wanted in the first place. So a lot of these things are really simplified if you use Kudu for this use case. Essentially, all you're doing is you're bringing all of your messaging data directly into Kudu. If you don't need to do ETL, for example, if you're just storing these records and then reporting on them, then essentially you can have your reporting system, maybe it's a SQL system, or maybe it's Spark or something else, basically just do some kind of a range query with some predicates, like select something where where your dates are in a certain range, and it'll just return it. So you have one system, there are no jobs you have to schedule, there's no trickiness with the late arrivals. So it's kind of nice, this kind of use case. I want to talk about one more use case, a real world one. So we're working with a company called Xiaomi. A lot of you have probably heard of these guys. They're the most popular smartphone company in China. They have a ton of customers, and they have a really big use case. Essentially what they're doing is they're gathering events that happen on cell phones and on their mobile services, and they want to basically do monitoring on these things and have a real-time inspection capability in order to do troubleshooting and look at individual records of individual services or individual users in order to figure out what's going on when they detect a problem, and they want that available immediately. They also want to be able to monitor their services to know if something's going wrong. So they have billions of records a day coming in, and they want the data available immediately. Their previous architecture looked like this. Essentially, they had a bunch of applications coming in. These data sources are actually a bunch of disparate data sources, and they were writing simultaneously into HBase and Scribe, which ended up writing sequence files to HDFS. So this top database looking thing is HDFS. By the way, I should give a shout out to the Xiaomi guys for providing these slides. Thanks to Bing Lin. And then an ETL job would merge these things, and for stuff that needed essentially so there were basically two paths. And one path would go to Parquet in order for sort of long analytical jobs, and for dashboard type jobs, then it would go on a different path. So there were a couple of problems with this. One problem was that there was a really high data visibility latency. So it took from an hour to a day sometimes for the data to show up. And it's tricky when you're dealing with all these data formats. You have HBase, however you're serializing stuff in HBase. You have your sequence files, you have Parquet. Converting between all of these can be really hard and have like a bunch of edge cases that you have to deal with. The other problem was in order arrival. They have these offline mobile devices. They're not always online. Maybe you don't have data for, maybe your phone's dead overnight, or maybe you don't have a good connection. And so periodically it's going to update stuff, upload stuff from the past day, for example. Then they'd have to basically read a bunch of days and assume that included all of the data that they were interested in.
So, if this was a purely analytic use case, why were they putting it into HBase? Were they also accessing, like you said, HBase is used a lot for single row access, right? So were they accessing the data as it's coming in as well?
Yeah, I think this is probably a missing an arrow from HBase to the result serving, so the dashboards could look up records directly.
Okay, got it, thanks.
In here, essentially, what they've done with sort of post Kudu is use Kudu as the primary data store, use Kafka and Storm for data enrichment. Maybe they want to enrich records as they come in. Maybe they only have a couple of IDs and they want to add more customer data or service data or something before they store in the database. And then they're using Impala for the tricky queries, for the big joins and big aggregates and stuff like that. And then they're also using direct access via the NoSQL APIs to Kudu for their dashboards. So they really reduce their latency for the ETL pipeline, while also getting essentially a zero latency path for applications that can handle back pressure by writing directly to Kudu, and that don't need enrichment of those records. So, okay, this all sounds great, but how did we make this happen? How does it work?
So what is your page format over here? Are you using some like variant of Parquet or?
Internally, how are we storing the data? So I don't have it on these slides because I didn't think I had time, but let me come back to that. I'll answer that, and then I'll give you a pointer to the details. We have a white paper that goes into a lot more detail. Since Kudu is a cluster-based system and it's part of the Hadoop ecosystem, it needs to be fault tolerant, and it needs to be able to handle when a machine crashes without becoming unavailable. So the way we handle replication and sharding is you have one big table and we do horizontal partitioning. Kudu can partition either on range or on hash or a combination of the two. So range partitioning is what HBase does. Maybe like the first 1,000 rows go into region 1 and the second 1,000 rows go into region 2. Kudu can supports the same thing. We call those regions tablets, but effectively you have your big spreadsheet and a certain rows go to certain tablets. These tablets are hosted on what we call tablet servers. The tablet server is just a daemon that runs on a machine, and that tablet server hosts a bunch of tablets. So like at this level, it's pretty similar to big tables design. We also support hash partitioning, which is really nice for stuff like time series use cases, because effectively you can use the time and potentially also some other compound key as your or some other fields, your compound key, and you can avoid hotspots by hashing those.
So ultimately the goal is to same server storing having the data node, region server and tablet server on the same node. That's what the architecture is, and a worker node.
Yes, you can do that. You can have you could co-host HDFS and HBase and Kudu on the same machines. So each tablet has a certain number of records. We're using Graph Consensus. Graph Consensus is similar to Paxos or similar to Zookeeper. I'll talk about it briefly in a minute. We also have another process called the master process. It's a replicated master, and it basically handles coordination. So it acts as a tablet directory. It tells you which tablets exist, where they live, who has replicas of which tablet. It also acts as a catalog, which tables are defined, what their schemas are, what the encodings of those columns are, and stuff like that. It also acts as a load balancer. So if a tablet server dies, then it will, after it detects that that tablet server is permanently down, it'll re-replicate the data on that tablet server to some other tablet server. The master is also very fast because we're able to cache all the metadata in RAM, and as a result, we get really low latencies for master lookups. So there's not really that much data that it has to hold in RAM, and so we did, as an example, we did a stress test where we created a bunch of tables on an 80-node cluster. the 99% latency was under 100 microseconds. So it's really fast. The client talks to the master and fetches the metadata from it, and then caches that data. So where the tablet's located, and it doesn't go through the master to write the data, so it's not a bottleneck. No data is ever written to the master, it's just metadata.
What if the master goes down? How do you handle that?
The master uses the same kind of graph consensus replication as the tablet servers. So the master is actually just a special tablet.
So it is not similar to name node in XPS.
I think it's analogous to the name node, but the details of it are different, and we think that it'll scale up to thousands of nodes. Whereas, as you may know, the name node is currently sort of hitting its limits at thousands of nodes, and so we're looking at different options to increase the scalability. We don't
I'm
think
just
that.
trying to figure out in which environment you can configure name node as HA, right? So in this case, how do we configure high availability? Is it similar to name node HA or?
Oh, yeah, in many ways it's similar to name node HA. So name node HA uses Zookeeper, and the Zookeeper protocol is similar to the Raft protocol in sort of its function. And so it's highly available by design.
Quick question.
Okay.
In the previous slide, you have the hash table, hash into the 100 buckets.
Yeah.
How do you handle, the creations? How do you handle the expansion of the table?
Right,
you
so how do we
list
split
to expand
tablets?
it, or?
So today, as of today, there is no splitting, so you have to pre-split. That's a feature we're planning on adding. It's just not implemented yet.
So you were saying you can't repartition. The number of shards is constant.
The number of shards is fixed until we add that feature. If you need to reshard, then you have to copy. You could do like a create table select from.
That's like a new table.
You create a new table and you copy all the data over. Exactly. That's currently the only workaround. Yeah.
When you say it's multi-master, so it's what, like, there's, it's like master-master architecture, and is that per, like, data center, so is it, like, let's say you have 3 masters, are they all in the same data center, or can you allow masters to span the way out?
Right now, so geo-replication is compatible with this design. There are still some features we want to add to make geo-replication work well. So I guess the answer is long-term geo-replication is definitely in scope. Today, there are some things that would probably make it hard to operate. So let me give an example of sort of how this replication works. So here on the slide, on the top left, you have the client that's talking to Kudu, and it has its own little cache of the metadata in that little cloud thing. On the right, you have the master. It's a replicated master, so it's sharded across 3 master servers. One is the leader and 2 are followers, and that's how Raft works. There's a strong leader in Raft. So in the middle, you have tablet servers. We're showing 4 tablet servers, and we're showing 3 tablets here. So those 3 tablets span different tablet servers. So if I want to update a row called Percy, or that's a key of Percy in table T, then what I do is I talk to the master if I have a gold metacache, and I say, hey, I'm the client, can you tell me where this key lives? And the master is going to respond and says, yes, this key lives on tablet 2. And it won't matter, I'll give you the rest of the metadata for the table. And then after that, then the client can do unlimited updates of that key without ever talking to the master. And the client just goes directly to that tablet's leader, and does the write. And what happens in the background is that leader will then replicate to a majority of the cluster and respond.
So are the followers readable or?
Yes, the followers are readable.
They are also writable. I mean, the
No,
client
only
has
the leader is writable.
it's more like a Kafka replication.
I don't think Kafka uses exactly
Master
a
leader and
consensus
leader and
replication,
follower.
but it's pretty close. So like, I think Kafka, I'm not totally familiar with how Kafka does this replication, but I think it tries to write to all replicas. So they have some kind of access like that.
So does the client cache where the row is when it returns from the master?
Sorry, say it again?
So does the client cache when it returns from the master tablet? The
Yeah,
information?
yeah, sorry, the graphic is a little silly, but yeah, this is supposed to be like caching those rows in that little cloud.
And if there's a change, it'll fail, it'll then go back to ask again.
Yeah, if it detects it's wrong, or there's an error, then it will go back to the master and request fresh metadata. So that it's allowed to be out of date, and it'll just hit some error like this tablet doesn't live here anymore, and so it'll just go refresh.
Is there any push of the metadata or it's always a full?
It's always a full.
Always.
And what is the synchronization latency between master and follower?
It's pretty fast. Excuse me. The heartbeats are pushed actively. So if there's a metadata update from the tablets to the master, then if there's a change, we will immediately heartbeat. Otherwise, the heartbeats happen every half a second, just to let the master know that the tablets are alive, and also do like block reports and stuff like that. Or not block reports, but basically tablet reports. So similar to HDFS's block reports. So the fault tolerance, as I said, we use graph consensus. It's a strict quorum algorithm, which means you have to write to a majority, and a majority can't go down. If a majority goes down, then you have to bring one of the servers back up and reclaim that majority in order to continue your writes. So on transient failures, if the follower fails, then you don't really notice, actually. Unless you're trying to read from that follower. If you're trying to write to the leader, then as long as there's still a majority, the tablet still continues. If the leader fails, then there's something called a leader election that takes place. And basically what that means is there are a bunch of the nodes that are members of that tablet decide, okay, hey, I haven't talked to this leader in a while. Have you talked to the leader? Maybe we should elect a new leader. And so that happens within a few seconds. That the decision is made to elect a new leader, and then another couple of seconds, and a leader will be elected, and it will be available again.
So is there a centralized way of detecting failures, or is heartbeat
It's
across
just-
everybody?
It's not centralized, so the heartbeats occur between members of the tablet configuration.
So, sorry, you said the writes are quorum, right? What about reads? Reads are quorum as well? I think you said that in there.
So so the quorum replication happens essentially in the background. So reads and writes are not quorum from the perspective of the client. Like if you think of Dynamo or Cassandra as a model, you only write to the leader, and you can read from anybody. If you want a strongly consistent read, if you want like the latest stuff, then if you want that guarantee, you do have to go to the leader, or you have to wait for that replication to take place.
Sorry, to follow up. In the previous slide, I think you had mentioned this as well. The client is topology aware, right? Like it knows the network.
Go ahead, Greg.
Okay, yeah, so what I was saying on the previous slide, just to build on this, reads and writes, the client is topology aware, correct?
Yes, the client knows where the different keys would be mapped. And it gets that information from the master and caches it.
So if it's a range scan, you broadcast?
If there's a range scan, then you...
Range query, I mean.
Right, then you contact one replica from each tablet. Like if you want to scan the whole table.
Well, I want a range really, but
Yeah, if you want a range scan, then then we'll prune those ranges. We'll do range pruning. So you only contact the people that are in your predicate.
Yeah, but then you don't know what are all the possible values in that range, so you're not going to go query the catalog for each of the possible values in that range.
Oh, right. Yeah,
So it's a
if
broadcast
you're-
typically.
Yeah, it would essentially be a broadcast if your predicates.
If it's not range partitioned.
If you can't, yeah, if you can't.
Obviously. Yeah.
If you can't determine, if we can't prune the range based on the
Yes.
primary key.
Sure.
The client will block till the colon is met, right? Is that, so
Yeah,
it has to be replicated
Yeah.
in insert has to be replicated.
The leader will not respond until to the client until it's committed, until it's core committed and applied actually. Or it may actually be able to respond earlier than it's applied as long as it knows that it'll be successful in applying it. So. Okay, one last question and then we'll move on. Yeah.
Can I summarize like this? This Kudu is something with a combination of zookeeper and database.
It's very hard to hear.
Oh, the question was, is Kudu a combination of Zookeeper and HBase? I guess no, but maybe I'll be able to answer that better in a moment. So a big part of why Kudu is fast is it uses columnar storage. So let me talk a little bit about that. Essentially, imagine that you have a Twitter Firehose table, you want to do some data mining on Twitter. Now you have this table that looks like this. You have tweet IDs, your username, and the text of the tweet. Now the way Kudu is going to organize this, it's going to put all the tweet IDs together in effectively the same file, or at least the same area of storage. They'll be adjacent to each other. Same thing with all the other fields. So this is what's known as columnar storage. What it allows you to do, if you're running some analytical query, you want to say, hey, give me a count of all the tweets from Hacker News. What this is going to do is it's going to basically, instead of having a row store may have to go and scan through 205 gigabytes of data in this case in order to determine that, in order to get this count. But a column store is actually much more efficient in this case because it only has a where predicate on one column and then it's doing a count. So it only has to read 2 gigabytes of data, which means that it's doing less I/O and it's just going to compute faster. In addition to this, columnar formats that have a strong schema are also really good at compression. So if you have a bunch of timestamps that are most likely on the same day or very close to each other, they're not going to be decades apart, then you really only need a few bits to describe those deltas. So that means that instead of 64 bits per row on this column, we may need 17 bits per row on this column. So all of these columnar tricks are really applicable to things involving time or like enums, low cardinality strings. Kudu supports a bunch of different encodings that makes scanning these things and storing these things much more efficient.
Question. So you use the local file system directly, right?
Yes.
So, and these are true columnar stores, no
Yeah.
paxes? No pax, so every column gets a separate file,
Oh.
It's not that simple.
okay?
But you can think of it like that, but you probably shouldn't think of it like that because you probably would know that would cause problems on the file system essentially.
So you have column
scalability
groups?
problems. So we have another layer in between. We do run on ext4 or XFS, but we have another basic block storage layer that puts a bunch of columns in the same disk file, but you could think of it a lot like having a single file, just with different scalability characteristics. We won't run out of inodes like you would if you were doing something like that. Yeah.
Is it possible to index on columns different than a date column, or like sharding other than a date column?
Yes, you can. There are no secondary indexes right now, so it's your primary. Your index on your primary key.
And it is only a date column? Should be a date column?
No, you can use whatever schema you prefer. So actually, I'm pretty much hitting my time limit, so I better hurry up to the rest of the slides. So handling inserts and updates. So this is what you asked about earlier, Mohan. I'm going to just point you to the paper on the details.
Okay.
But essentially, there is something Vertica calls a write optimized store and a read optimized store. We have similar concepts.
Okay.
So we have a write ahead log, similar to a database transaction log. You write to the write ahead log and then write it in memory for your inserts and your updates. And then those periodically get flushed to disk in a format that is efficient to scale. So that's the high level thing. And then
the required and then you do the update statement. We are implementing a CDC mechanism. We are implementing a CDC mechanism and trying to see what is the throughput, to make, let's say, 100,000 updates in a span of a minute or 2 minutes.
Yeah, I think it probably depends on a bunch of different factors, but I'll show some benchmarks that shows what it's competitive with. In a moment.
The
So
scans can see the in-memory store data? Or do they have to wait?
The
for
scans
the-
can see everything. Yeah, exactly.
They
It's
don't wait
Kudu
for-
handles all of that kind of, view merging type of thing. The client doesn't ever have to know about it.
But updates are basically handled as inserts followed by deletes.
No updates are handled as deltas.
What does
They're-
that mean? Meaning, like if I modify only one column, are you saying you're keeping?
We'll just keep that,
Oh.
and then eventually compact it down. So I'd like to talk about the integrations and then quickly run through some benchmarks. So the integrations that Kudu has today are Spark. So there's a Spark data source written by Ted Malaska. We haven't merged it upstream yet, but the usage is kind of nice. So check it out, and we're working on merging it into the main tree. There's also Impala integration. Impala is actually probably the easiest way right now to try Kudu out. If you have a bunch of data right now in a table like on HDFS or CSV files or in Hive, then you can basically just say create table, distribute by blah 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 as a Kudu table, as select star from this other table, and it'll load the data for you. And then you can play with your own data and see how it performs and stuff like that.
What's the API for Kudu? Is it like SQL or is it like a C?
There's a NoSQL API, but then these SQL engines can interact with it and provide that for you.
ILOS supported?
Hive's on the roadmap.
So I'm a bit confused. So what's Impala versus what's Kudu? I'm confused by
Impala
this.
is the SQL engine that calls Kudu
As a
APIs
storage.
as a storage engine,
I see.
and in many ways the same as something like Drill talks to HBase. So the Drill connector is very similar to the HBase one. We can handle predicate pushdown, scan parallelism, locality, a bunch of stuff like that through those APIs, and it's all hidden behind SQL. We also have MapReduce integration. All of our stress testing is typically done through this, so it's pretty solid. We have a lot of confidence in it, and it'll also allow you to do predicate pushdown, column projections. So the performance stuff, since this is kind of why we built it in the first place. I have a couple of benchmarks that I want to run through real quick. One of them is TPCH, which is a kind of a standard data warehousing style workload. Queries look like this. They're pretty crazy looking. It's like a bunch of 5 joins and a bunch of stuff going on. We ran this on a 75 server cluster with 12 spinning disks and enough RAM to fit the data set. And it's TPCH scale factor 100, which means a 100 gigabyte data set. So this is essentially kind of an eye chart here, but the real takeaway here is, if you remember at the beginning of the presentation, I was talking about how we wanted to get within about half of Parquet's performance, since Parquet is generally considered one of the best data formats for Columnar analytics on Hadoop today. It turns out that we were pretty happy when we saw this. We were a little surprised. We were outperforming Parquet by 30% on average, and we think that's 2 reasons. One, we can do range pruning. Also, we can do lazy materialization. We can divide predicates without materializing the whole row.
So you said the RAM is enough to fit the entire data in memory, right? So is
Yes, on
any of
this-
the IO, is any of the IO even taking in for any of all the Columnar store that we talked
Yes.
about? Is that even kicking in?
Yes, this is all flushed. So this is post-flush. So it's not using the row-based representation in memory. This is all flush disk. But you are right that this benchmark, these benchmarks that I'm going to show, have the files cached at the OS level.
There's one more reason that this is slower.
That's another reason that
Parquet's balance, Parquet's gallery is very slow. It doesn't code generate, whereas
yeah. Parquet would probably do better on disk because it takes bigger bites of, I don't know. Yeah.
A question, if you did any TPCH with oracles in memory store?
No, actually, if we did that, then, and I showed it to you, they'd probably sue me.
Smart.
You're not allowed to do that. But you can do it, and, you know, post it on the
So you,
Let us know.
Well, they're available publicly because the Oracle did TPCH with compared it to SAP's HANA.
Yeah, but Oracle has a DeWitt clause, right? So, like, they can do whatever they want.
Oh,
They
yeah.
can't do whatever we want. And we also compared against Phoenix. Now, it's not a totally fair comparison, but it's an interesting one. Phoenix is really an OLTP style store, which is really optimized for individual record access. It's built on top of HBase. This is a logarithmic scale, so it's an order of magnitude improvement for each one of these lines. And you can see that for loads, we did a little better than Phoenix, but Parquet is much more efficient. For all the other stuff, TPCH query 1, just account star, account with a predicate. Kudu's pretty much beating everything else or about on par with Parquet. Maybe it's like 100 times faster than Phoenix for these kinds of things. For single row lookup, it's a little weird because logarithmic goes negative when you go less than 1, but Phoenix is way faster than Kudu, as expected on single row access, because that's really what it's built for. YCSV is the last one I just wanted to show really quick. The main takeaway here is that it's pretty similar to HBase. For Zipfian style workloads, where essentially it's power law, so a few rows are getting all the updates basically, but it's still random, so it's a long tail distribution. We suffer a bit, and I think that has to do with the deltas that we're applying, or we know that's the case. There's some low-hanging fruit that we can address there, but this is a linear scale, so effectively on a lot of these use cases, this is more of an LTP style workload. We're pretty competitive with HBase. So that was the meat of the presentation. I just want to give a high level on status, where the project's at, how to get involved, where to find the code, stuff like that. So Cloudera first open sourced the project at Hadoop World this year. That was version 0. I got a little message from chat and that didn't show up. Not that it was bad or anything. So 0.5 was released in September. 0.6 was released last month, and so that's basically just a few bug fixes that we and a couple of like additional tools and small features and polish. So today it's pretty usable actually. We haven't had a data loss bug so far. So we think that's a good sign, but maybe other people are just like smiling about that. But these are database people, so and we think it's reasonably stable. So we've had almost no crashes reported in the field. There's still some tweaks that you probably might want to make, and you might get our help to make them, or in a way that you get the performance that you want. So, and you might find some bugs, mostly minor ones, but anyway, so caveat emptor, I guess, it's still data software. We are, as of last week, I believe, we're part of the Apache Software Foundation Incubator. So it's now super open sourcey, and if you want to, we'd love to have additional contributors. If you want to be a committer, you can, and we'd love to have more contributors to this project.
One question.
Yeah.
Is there any possibility that you and Harkenworks can work on this?
I'll repeat the question. The question was, is there any possibility that Cloudera and Hortonworks can work together on this? And yeah, we hope so. Actually, we reached out to them right after we announced this project, and sort of the back channel thing that we got back was, yeah, maybe if it's an Apache project. We intended from the beginning to make it an
We need
ASF.
more than from you, we need more than hoping. We need some initiative from your side to bring that. Because for the past 2 years you guys are going like this. If you want to depend on this to build it cool, it has to work. This is very, very good technology, definitely.
So we definitely, we can get into this more maybe offline, but basically we want this to be an inclusive project. The current community, essentially, these are companies that are either currently evaluating technology, finding bugs, like using it as users, or are contributors. Dropbox is currently filing bugs and talking to us about some stuff, and helping us. They found an interesting bug that we fixed in the latest version. Xiaomi, of course, as I mentioned, as a user, they're also a contributor. Intel has done a bunch of low-level performance improvements, as well as integration of their NVRAM technology as the block cache, and Dromio integrated.
What did you say about NVRAM?
Oh, Intel is currently working on NVRAM integration with Kudu for its block cache. And also, I mean, with NVRAM, for example, if you put the right log on NVRAM, like the whole thing is going to speed up. And if you put the blocks on NVRAM, the whole thing's going to speed up.
So is that for getting more memory per node, or is this for real persistence of the data?
It's for keeping the blocks hot. It's for keeping the blocks hot across like restarts and stuff like that.
For persistence.
Yeah, for persistence.
So to get started as a user, just visit our website. It's getkudu.io. We also have a mailing list and a Slack channel. So we hang out there every day. So just feel free to join and ask questions. If you have any problems or just want more information, then you can reach out to us. There's a quick start VM of Kudu that makes it easy to just get it up and running as a VirtualBox VM or something like that. There are also parcels that makes it really easy to install on a Cloudera managed cluster. They're a Cloudera manager managed cluster. Otherwise, we also have dev packages and RPMs. As a developer, if you want to get involved, all the code is on GitHub. We have a public Git. We don't do code drops. There's no like batch updates. All the development is in the open in real time. And we have a public Jira. We essentially had a private Jira that we then took public. So you can see like our dirty laundry back from essentially the beginning of time as far as Kudu is concerned. So any code commits that reference Jiras are available. Because we had intended from the beginning to basically do the design, get the kernel of something interesting, and then make it an open project. And we also have a developer mailing list. So that's it. That's all I had. So please feel free to reach out to me. Visit the website, and we'd love it if you follow Apache Kudu on Twitter. Okay. It sounds like we have. Okay. It sounds like I have time for questions. It sounds like we have time for questions.
Yeah, but I would just like us to use microphone to hear the question and then you can answer.
Sure. Yeah. So please raise your hand and Shasha will bring you the microphone.
So the encodings for the Columnar store, are you keeping them global dictionaries, local dictionaries, public data?
Today we're not using a global dictionary for the dictionary encodings. It's per tablet.
Per tablet and tablet.
It's actually local on the node.
Two questions.
Yeah.
First, how do you see this is different than Druid, if you know Druid?
Yes.
And the second question is there any goal for Storm or any way to integrate with the edge base for Storm?
Sure. So I think integrating with HBase is probably something that needs to happen at a higher level. I don't think Kudu as a storage layer will ever directly integrate with HBase, just because they are pretty different systems. Kudu's written in C++ is one reason. And they have like in many ways different use cases, although there's some overlap. As far as Storm goes, we'd love to have contributors that can integrate Storm with Kudu. So if that's something that you want to see happen and you want to contribute that, then we'd be open to it. That's not on like the Cloudera roadmap, or that's not like I'm not planning on doing that personally or anything like that. But we're totally open to it. As far as the Druid question, expert on Druid. I unfortunately missed a talk about it recently, but my understanding is that Druid doesn't have the same level of like mutability as Kudu, but I'm not an expert on Druid, so sorry I can't go into detail.
Anyone else? Oh, you're next.
Oh, I lost it.
This is a little generic question. Do these data analytics, this application for the Apache Kudu is essentially focused towards data analytics, is that correct?
Yes.
And do these work on standard storage? People who use the enterprise storage stuff, do these Apache Kudu works in conjunction with that also, or it works only with Hadoop kind of data storage?
You mean like a NetApp or something? So, I don't think it kind of depends on what the architecture of the underlying disks looks like and what kind of bandwidth you have. But I think at the end of the day, if you're using shared storage, at some point you're going to hit a wall relative to like local SATA bandwidth across the cluster, like on a single node, as distributed across the cluster. That makes sense. So this isn't tied to Hadoop itself. Actually, like Kudu doesn't really have any other service dependencies, as actually dependencies, but no service dependencies. So Kudu can run by itself on local disks, and then all the other systems can directly access it. So I guess in most cases I would recommend against using shared storage. But if the shared storage is sophisticated or fast enough, then I wouldn't say it would work.
So let me ask my question again about the page format and how different it is from Parquet and why.
No. Oh, sorry.
Page format.
Page format.
Oh yeah. Okay. So internally, Kudu uses a format that it calls C-file, and it's very similar to Parquet actually. It's effectively Parquet plus additional indexes to do single record access and support deltas. But like at its basic level, the individual C file that represents a section of a column in Kudu is pretty close to a Parquet file.
When do you think we can implement this in a project?
Let's go over here.
It's not on the patch format, it's more columnar than Packer. You don't have the 64 megabyte block that you have all the columns of the table.
Oh, okay. Let me answer this question real quick. So we have what we call it's like a log block container. We kind of have like a log based container that you essentially like write your data to some file. You stream as you flush a bunch of stuff to like the end of some cursor in some container. Essentially, just like keep appending that container until it's full, and then we'll use hole punching if you end up being able to like delete whole blocks. But we are essentially allocating like a certain amount of space per what we call a block, and then so the column will sort of go to a certain point, and then you might have to seek somewhere and then get sequential access.
The point is that in a single block you do not contain all the columns of a single of a set of rows.
Oh yeah, we'll allocate space for like a whole column and then space for another column. Yeah, so that would make it like.
But they're still part of the same file, or they're in different files, the different columns?
Oh, that's the question.
Yeah, I asked
okay. Oh, I see. Then I actually think. I actually don't know how to answer your question.
I think it's different colors.
You don't know?
I think actually now that I think about it, we try to select different containers, and I don't know what guarantees we have on like the containers of data, but we do try to select different containers, different columns, so that you can scan them all simultaneously.
That was the concern.
Yeah.
So what is the different file?
Okay.
Sounds like it's different files.
Talk about not exposing the timestamps that you use, but you
Right.
you said that you can use a timestamp from your recording.
Yeah.
To do sort of like a version use case so that you can see what something looked like year over year.
Yeah.
Is that possible automatically, or we have to build that into the key?
So as of queries is what you're asking,
Yeah,
right?
exactly. If I change something 10 times in a
Yeah, you can. So you can query. You can query at a timestamp, but we don't allow you to assign a timestamp.
So how do I know what timestamp I should query on?
You can. There are APIs that you can get the timestamp at. So if you're using like the NoSQL API, then you can essentially find out at what time something was written, and then you can do some kind of like commit wait kind of a thing, or you can like query at that timestamp.
Any more questions? We can take one.
So that's the question. Is this time?
Yeah, here you
You now, the
Oh,
last
sorry.
question.
Okay. Is the timestamp something that's like a clock on the wall kind of timestamp that somebody can, in a common man sense relate to, or is it some gobbledygook?
It's there are actually a few different timestamps that we support. In general, really only two that would make sense. One is just a sequential like logical clock.
So that's not meaningful in that sense.
Right. And then the other one is something called hybrid time, which essentially enables us to use a combination of real time synchronized across members of the
Cluster.
of the cluster, of the tablet configuration. I want to say quorum, but like whenever I say that, people can matter. And members of the configuration, and then the other component is so it's basically real time plus logical time together. And what this allows you to do is essentially keep these nodes synchronized. And so there are more details in the paper around how hybrid time works.
Thank you.
Thank you.
Great. Thanks, guys.
Great.
One last question.
Okay, we gave him one last. Yeah, hold on a second.
When do you think you can start implementing our projects?
So it depends on the level of stability. Today, it's fit for proof of concepts and for planning next generation architecture projects. If you want something that, for example, a company like Cloudera would support in the field, then I think we're looking at something like a year out. So like GA, Kudu 1.0 kind of thing. We are currently thinking we want to deliver this in 2016.
1 year from now, GA 1.2.
Thank you, Mike. First, I want to thank you all for being so engaged. I can't remember an event in the last year where people have been so engaged. So thanks, Mohan and everyone else here. And I got, if you another answer to your question about the Hortonworks thing, there's a guy here called Justin. I'm sure he has a solution for you. So thank you all, and we look forward to seeing you. It's probably January 20th, and it's going to be on Kafka and other sort of streaming type of things, with Confluent and with the Apache Hadoop guys and so forth. So look forward to seeing you there. Thank you, guys.